Okay. Hello, everybody. Um, my name is Leo. I'm one of the two TAs for EE102, and I get to play Professor today because Professor Boyd is giving a talk in Michigan, and he'll be back by Monday. So, okay. I should just tell you this is the first time I give a lecture like this, so if I get nervous or make mistakes, well, I hope you understand that. I have a couple of announcements. The first of which is that we have a quiz today. I'm sure most of you know that, but I want to say that just in case you were planning to take a nap at the end of class, which has happened to many of us recently. And the second is I want to also point out that we have a few typos in this lecture here, so I wish to correct those as we go along. So keep an eye for those. Let's see. Can I get a show of hands for those who are confused by the material in this lecture, roughly? Okay. All right. That's great. Okay. So the plan for today is hopefully to finish Lecture 9 on Bode Plots. Okay. And so I want to start with a short review of what we've been doing. And look. Okay, we're centered. Okay, so the basic question of this lecture was what happens when we input a sinusoid at time 0 into a system with a transfer function h, okay? And we found a neat result. It was the following. It said the output really has several components, one of which is the sinusoid itself at the same frequency as the input, okay, and differing possibly only in the amplitude and the phase, okay? And there were some other terms. Now, if the system H is stable, these other terms are guaranteed to decay to 0 eventually. So if we wait long enough, all that we're going to be left with is the sinusoidal term. Okay? This same thing holds when the system is unstable, except now these other terms don't vanish. So it really doesn't make much sense to talk of the frequency response when this term here is eventually swamped out by these other ones. Everybody with me? Okay. Great. So for the case where the system is stable, these other terms, which we know decay to 0 eventually, is what we call the transients. Okay? All right. And so the next important result was the determination of how A and phi, this amplitude and phase terms, depend on the characteristics of the filter, or I should say, the system. Okay, and the result is really quite neat. All the information lies on the transfer function evaluated at j omega. The amplitude term, or the gain, is given by the modulus of the transfer function, and the phase is given simply by the angle or the argument of the transfer function evaluated at j omega. Okay? So the neat result was, in order to find out the frequency response of this system, okay, what we have to do is evaluate the transfer function along the imaginary axis. Okay? Right here. So if we want to find out the frequency response, all we have to do is find some way of moving along this line and determining the modulus and the argument of the transfer function. Okay? Everybody with me? Okay. So the next obvious question is, well, how do we plot these frequency response? And we talked about a couple of them. We talked about Nyquist plots, and we also talked about Bode plots, which are the most popular ones. Nyquist plots will come up, especially if you do feedback control design and so forth. Bode plots show up everywhere because they're so easy. Okay? And so the basic idea of a Bode plot is that it consists of two subplots. They have a common horizontal axis, which is the frequency on a logarithmic scale, okay, right here. And then on the first plot, we have a magnitude, okay, plotted on a decibel scale. So this one here. And then for the phase, we use a linear scale. Okay. The reasons for this choice, I think, will be explained two notes from now. Okay, so let's keep this in mind. So the starting point was, actually no, I should say, yeah, the next question is how do we go about plotting these in practice? And Professor Boyd emphasized that nowadays we use MATLAB to do this, or any other piece of software. Okay, in MATLAB it's so incredibly easy to make a Bode plot. All you have to do is specify the transfer function in one of several ways. You could specify the numerator and denominator polynomials that give you the rational function for h. Okay, or you could also provide the zeros and the pole locations. You could also provide the residues and the poles. And there's other ways that we actually haven't covered in class, okay? And so whatever representation you choose for h, doesn't matter. MATLAB is so smart and so cool. It'll plot the Bode plot for you instantly, okay? But Professor Boyd emphasized the importance of being able to make these plots, okay? So today we're going to play this game of plotting Bode plots by hand. And the idea is to be able to draw the frequency response almost by inspection. So we're going to make some really simple approximations whenever we can't really determine the contributions to magnitude and phase exactly. Okay, so let's get started. To do that, okay, our starting point is a transfer function written in this factor form. Okay, the reason for that is that from this form we can tell at once what the zeros and the poles are going to be, right? And there's a very simple graphical interpretation as to the magnitude and phase of h in terms of the zero and pole locations. Okay, so to get to that, all we have to do is rewrite s minus z1 using this representation. This should be very common to everybody here, right? This is the argument, and this is the modulus of this complex number, okay? The graphical interpretation is really quite neat. The magnitude of this term here is given by the distance from, okay, I did it here for a zero. So the distance from the zero to the point of interest, okay? So I've chosen my point S to be on the j omega axis for obvious reasons, okay? And so it's all here. The magnitude here is given by this distance, and this phase term is simply the angle between this vector, s minus z1, okay, and the horizontal line. Okay? So if we rewrite every term here using this representation, we end up immediately with this. Okay? And this is really kind of neat, because this tells you, look, the phase of the transfer function, evaluated at s, okay, is given by the sum of the contributions from each of these terms above. Okay? Oh, I'm so sorry. Gotta keep it. Okay. Okay? So each term adds its own contribution, and so to find out the net phase, we just add them. It's not so easy with the magnitude, right? Because here we have all these product terms. Aha! But there's a really easy solution to this problem. And the answer is to write the magnitude on a dB scale, on a logarithmic scale. Okay? So that's the next step. So, here we go. So we take the logarithm of the magnitude, okay, and we end up right away with this expression. Everybody with me? Okay. So here it's really kind of neat, because now, again, each term here is the contribution of one of these terms, s minus z1 or s minus p1 or so forth. Okay? So in order to be able to plot Bode plots, all that we have to know is how to get the Bode plots for simple terms, like the simple scaling term here, okay, a set of poles or zeros at the origin, a real pole, a real zero, okay, and a complex pole pair. And similarly, I didn't put it here, but a complex zero pair, okay? And from here, from this so-called sum property, okay, we can justify the choice of scales for the Bode plots. Okay, from here, okay, we can understand why we choose at least these vertical scales for the Bode plots. Okay, everybody understand that? All right. Now the choice for the logarithmic scale here, I think I'll point out shortly. Okay. Okay. So now we have to play this game. Remember, our goal is to be able to plot Bode functions, Bode plots, excuse me, very simply. Okay. And so the name of the game now is simple. We want to know how to get Bode plots for these different terms here. If we can get the magnitude and phase exactly, then great. But if not, we're going to simplify our life with very simple and actually quite good approximations. Okay? So this is the program for today. Everybody understand that? I should also mention one thing. We're cheating here at some point because our starting point is the transfer function given in this factored form. Okay? Now, I should ask you, well, how in the world do we express h of s in this form if we're given, let's say, the transfer function as a ratio of two polynomials? We have to factor these polynomials, right? And we learned early on that to factor anything other than second order is really quite a mess, right, for the third order. And in fact, above that, we really can't do it. So we're cheating here in the sense that in order to put the transfer function in this term, most often we'll have to rely on some piece of software to give us the pole and zero locations. Okay? So you might say it kind of defeats the purpose if you have to use MATLAB to do something by hand that really you can do with one line of code in MATLAB itself. Okay? But anyway. Okay. All right, so let's start getting some simple Bode plots for these terms. And so, let's see. Okay. Okay, from now on, I'll follow the lecture notes a little bit more closely. I'm almost done with my notes here. The first term is so easy that Professor Bode didn't care to put them in the lecture notes, right? It's just the k term here. It's really easy because there is no frequency dependence to the magnitude and phase of this term, okay? None at all. So really, the Bode plot consists of straight lines. It's a piece of cake. Everybody see that? Okay. Here we plot the magnitude. I made the k term be greater than 1, and therefore here I'm putting the line above the above 0. Okay, but if k is less than 1, you would end up here. Okay. The face is a constant. Similarly, it could lie below the axis if it were negative. Okay. I've just chosen. Okay. So that was extremely easy. That we could tell exactly. The next terms are the s to the k terms, where k is any integer. Okay, if k is positive, the interpretation is we have zeros at the origin, and if k is negative, the interpretation is we have poles at the origin. Okay, so let's get started with a simple example, which is k equals -1. Okay, that corresponds to a single pole at the origin. Okay, so now the name of the game is to find the magnitude and phase dependence as we evaluate h of j omega. Okay, for changing omega. And so the phase is really easy, right? The phase is given by the negative of this angle here, right? There's no frequency dependence, and therefore the phase is just a flat minus 90 degrees. Does everybody understand the minus sign in here? Oh, okay. Thanks. Yeah, this here is just my notation. All I'm saying is um, the vertical scale is 20 times the logarithm base 10 of the modulus of whatever I'm plotting. In this case, it's h of j omega, where okay, it's this here. Okay, with k equals 1, of course, for this specific case I'm showing. And so it's really easy to find the magnitude in the phase from here. If we look at the modulus, okay, all we end up is 1 over omega. Oh, I'm so sorry. I made a silly mistake. Here I put here we really have k equals 1. To be consistent, I would have had to write j omega to the k, right? I'm sorry. So therefore, here the modulus would be given by omega to the k. Okay. Okay. So for k equals -1, the magnitude here is given by omega to the k. Now let's put everything on the proper scales. Let's take the logarithms here that we want. So now if I find 20 log base 10 of omega to the k, right? Then that's quite simple. All I have to do is pull the k outside of the logarithm, and so what I end up with is 20k log base 10 of omega. Okay? And so remember, this is a variable for the horizontal scale, and this is our variable on the vertical scale. Okay? So notice we have a simple linear relation. So with k equals -1, our slope is -20. And so the frequency response, the magnitude, plot is really quite simple. It consists of a straight line. And the point of reference here is omega equals 1. For omega equals 1, you find always that the magnitude of the transfer function is 1. Okay? And that's true regardless of the value of k. Yes. A little bit louder? Oh. Maybe my mic is not on today. We were having problems with that. Am I on? Can you hear me better? Okay. Now? No? Okay. Well, I'll try and speak louder, okay? And if it's not enough, please let me know. Okay. Okay, so what I was just saying is that for omega equals 1, okay, the magnitude is always 1, regardless of the choice of k. And so for different values of k, can you tell me what the frequency, the magnitude plot is going to look like? Extra credit for anybody who tells. Just kidding. Well, the answer is quite easy. Here, the slope is -20 dB per decade for the choice of k equals -1. Okay. For other choices of k, the slope is given by 20 times k. Okay. So if I have two poles at the origin, I have -40 dB per decade, and the plot really looks like this now. Okay. Passing still through 1. Okay. If k equals 1, which corresponds to a pole, a 0 at the origin, okay, now the curve is upward with a slope of +20 dB per decade, like this. Let's see if I can do it. Okay, and so forth. And the phase here for k equals -1 is negative 90 degrees. To see that, like we did before, we just find this angle here and take the negative sign because the term appears in the denominator now. If we have k equals 1, okay, this angle is 90, but we don't take a minus sign, okay, because the pole appears in the numerator, okay? If you remember my prior expression. So for k equals 1, we have a phase of plus 90 degrees over here. For k equals 2, plus 180, and for k equals minus 2, we end up with negative 180, and so forth. Okay? Okay. Okay, so now we have two of the 5 terms of interest, okay? And let's go to the next easy ones. And those are real poles and real zeros, okay? So here lies our first typo. Here we start out considering the transfer function for a single pole at P, okay, where P is any real number. And the first mistake is here in finding the expression for the magnitude, okay? If this is a pole at P, then can you tell me what the transfer function should be here? What the magnitude should be here. So. Okay, the answer is 1 over this, okay? And so let's just go over that really quickly. H of j omega is given by 1 over j omega minus p. Okay? So now, the magnitude is given by the root of the sum, okay, of the squares of the imaginary and real parts, right? This term is purely real. So from here, we get p squared. And from here, from this purely imaginary term, we just get omega squared, okay? And so that's the correction there. And let's look at the graphical interpretation, okay? I actually repeat the same work here, okay? The interpretation is here that this term here, the root of omega squared plus p squared, is simply the distance between the pole and the point of interest, okay? The frequency at which we're evaluating the transfer function, okay? It's given by this distance here. So from this distance interpretation, it's clear what this distance should be from simple trigonometry, right? Because we have a right angle here. We go back to our friend Pythagoras, and we get it. So the phase term now is a little bit more complicated, right? We have to use an inverse tangent here. Omega corresponds to this here, and this distance here is given by the absolute value of p, okay? And so this phase phi here is given by the inverse tangent of, whoa, okay. It's so hard to look at this monitor and like keep it centered and stuff. I'm sorry about that. Okay, so this angle here is simply the inverse tangent of this ratio, right? Omega over absolute p, correct? And remember, we have a pole here, so we have to keep this minus sign when we're dealing with the phase of the transfer function. And so the transfer function is given by the negative of this inverse tangent. And so this brings me to the second typo here. Whoa. Thank you very much. Okay, so here, here's the problem. In this case, we have p less than 0, okay? We're just missing this term here, okay? Just an absolute value. So at this point, remember, our goal is to make simple plots, okay, on the choice of scales that we have for Bode plots. And it turns out, even though we have these expressions for the magnitude and the phase as a function of frequency, I doubt that anybody here can plot it, can plot the frequency response on the logarithmic scales and so forth that we've chosen for the Bode plots by inspection, right? Or at least I know I can't, for sure. Okay? So what we have to do now is play some games, make a simple approximation for what the magnitude and phase dependence look like, okay? So the obvious things to do is to look at the magnitude and phase at low frequency, okay? And also afterwards consider the limit of very, very, very high frequency, okay? And also consider, well, as we'll see, a very special frequency, which is omega equal to absolute p, okay? So Bode gave you the Bode plot for the for a pole at p equals -1, okay? So I want to go through the through how we can approximate this curve simply, okay? Okay. So let's do that. Let's talk first what happens at omega equals 0. So the magnitude of h at 0 is given simply by 1 over root p, right? Or 1 over root absolute p. Everybody with me there? Simple, right? Okay. The phase, okay, where's my... The phase at omega equals 0 is simply 0, okay? So at least we can understand this point here on the plot. Okay. Notice that for his choice of p here is -1. So 1 over root absolute p, p squared, sorry, is 1. And so the magnitude at 0 frequency is simply 0 dB, right? 20 log base 10 of 1 is 0. Okay? So we found this data point at least. Okay, cool. The next choice for omega is omega equals absolute p, okay? And here the answer is given again simply by simple trigonometry, okay? If this height here is root p and this base here is root p, okay, this distance here is simply root 2 of p, okay, and then, or absolute p I should say, sorry, and then this angle here is simply 45 degrees, okay? So, okay, so the magnitude, right, we just said was given by 1 over root 2 absolute p, okay? So it differs from the response at DC at 0 frequency by this factor 1 over root 2, okay? So, so we can tell exactly what the magnitude is going to be at this specific frequency. If it differs by a factor of 1 over root 2 from the response at DC, okay, then we know it's simply 3 dB below the response, okay? And here we have to remember our simple mnemonic rules, okay? The first is, yes, question. Louder. Oh, sorry. Okay, louder. Okay. Okay, to understand why it's 3 dB below the DC value at omega equals absolute p, okay, all we have to do is the following. Take 20 log base 10 of of this number here, okay, is tan of 1 over root 2 absolute p, and the answer is, yes sir, oh, sorry, okay, it's given by 20 log base 10 of 1 over absolute p, okay, minus 20 log base 10 of 1 over root 2, okay? All right, this term here, okay, is equal to 1/2, okay, 1/2 of 20 log base 10 of 2. Is everybody clear on that? Right. Okay. This here, remember, remember, if you remember from 101, we also mentioned this last time. This term here, when you actually plug it into your calculator, is very close to 6. Okay? 6.0 something. I stopped caring after the first digit, so for me it's 6. So half of 6 is 3. Okay? And so, let me see, okay. I'm confused by a minus sign here. Hang on. Oh, sorry. Okay. We should still have a minus sign here, of course. I've done two things at once, right? And I was careless. Okay. So, to go back here to our plot, okay, is we have now a new data point to consider. It's simply at omega equals absolute p, in this case 1, then the magnitude has gone down by 3 dB, and the phase now is exactly 45 degrees, minus 45 degrees. Okay? So, okay. As far as the magnitude is concerned, you notice not much exciting has happened between DC and the frequency absolute p, right? Not much has happened. Just a decrease by 3 dB. Okay. The final question we must ask, okay, is what happens for frequencies much higher than absolute p? Okay. So remember that 20 log base 10 of h of j omega is given by minus 20 log base 10 of w squared plus b squared. Okay? Okay. Now, for omega much greater than absolute p, then this term here we can rewrite as omega squared 1 plus p squared over w squared, omega squared. This term here on the right is going to be very small. Okay? All right. So now we use the logarithms, and we end up with this. Okay? This term here is simply minus 20 log base 10 of omega minus a small term here. Okay? Small correction. And so the answer is now, again, quite neat. It says that for frequencies much greater than the distance from the pole to the origin, okay, then we again have a very simple linear dependence between the variables we're using for the Bode plots, the magnitude in dB and the frequency on a logarithmic scale. Okay, and again we have a slope of minus 20 dB per decade. Okay, so the interpretation here is simply that for omega much greater than absolute p, we have this roll-off here at minus 20 dB per decade. Okay? And so now, at least we have a very good understanding, I hope, of what the magnitude response looks like. Okay? Because this is our approximation here, all right? And we evaluated these 2 points here. And so the simple approximation that people use, and it's given here on page 23, is, okay. Oops, sorry. Okay. The interpretation for the magnitude response is simply that we have a straight line, okay, at frequencies below the pole, and then we have a 20 dB roll-off, 20 dB per decade roll-off above the pole location. Okay, like this. Okay, and then we make a small correction here because we know at omega equals absolute p, we have this 3 dB correction to make. Okay, all right. So I don't want to go into the details of the phase, okay, but I do want to remind you that we know the phase for very, very large frequencies, okay, is going to be essentially minus 90 degrees, okay, because when we're out here, okay, way up here, okay, our angle here is essentially 90 degrees. At the farthest away we move, okay, along this line, this angle approximates 90, it approaches 90 degrees asymptotically, right? So this explains why the phase response goes to minus 90 degrees really far away, okay? And this is what happens exactly, okay, to the phase. We only evaluated 3 data points here, but the approximation we use commonly is the following. We just assume that the phase remains 0, okay, until a decade below the pole location, okay, then it falls off linearly, okay, and until a decade passed, okay, and then again it's flat out to infinity. This is our approximation, okay. And then if you want, you can do small corrections, okay. In the literature, you'll find many, 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 many rules for how to make these corrections and so forth. The answer is, I don't think we care, okay? At least for our purposes, we really don't care. When we ask you to do Bode plots in the homework and so forth by hand, these simple approximations are more than good enough, okay? Okay, wow. Time went so fast and I didn't get to do half the things I wanted to do because we have a quiz. But I want to, before we do that, I want to do something else. It's just note the distinction for when we have a 0, okay? And when we have a 0 at the origin, excuse me, when we have a 0, in this case, the choice was -1, okay? When we put a 0 here, okay, if you do the same analysis, find the magnitude in the phase and so forth, you notice that there's only one single difference. In this case, it's just that you don't put this minus sign. You don't have this minus sign to worry about. And so the magnitude really looks exactly the same, except now, no, it doesn't look exactly the same. It looks very different. But the difference is now, instead of putting that distance on the denominator, you just keep it in the numerator. So the distance keeps increasing. The interesting thing now is instead of rolling off at minus 20 dB per decade, your magnitude increases at a rate of 20 dB per decade, okay? And at the pole, okay, at the 0 location, you are plus 3 dB from the DC value. And then the phase now is the same idea. You start 0 here, and then very high up, you're left with essentially 90 degrees. Okay? And so this is what the Bode plot looks like for a simple 0. Okay? Now the thing remaining to do, and I think Professor Boyd will pick it up next time, is to talk about what happens when you have complex poles and zeros. Okay? Now the interpretation is really cool because the Bode plot looks more interesting. You get peaks and so forth, and hopefully he'll discuss the details of that on Monday. Okay? Okay, so time for a quiz, and I think we'll stop here, thanks.